Okay, welcome to my YouTube channel, Physics Matters. Today I would like to discuss another important quantity in physics, and this we call acceleration. Which is still part of kinematics. So what we can do in order to define this, first we have to find a good mathematical definition. Is when we take a look at the speed, this we have defined already before, and we said that this is actually distance over time. And in the same way, now we can define acceleration as speed change, in this case, over time. So we can also quantify this now with the help of the so-called VT diagram. This is always a very good thing to write down. So this is called VT diagram, and we have already seen ST diagrams for position and time, and now we do the same also for V, the speed versus time. And then we can again draw a few lines, for example an horizontal line, which means here our speed is simply constant and we have no acceleration. And we can also draw a few other lines, for example one in this direction and one in this direction. And now again here we have a constant slope, and we can also draw this triangle here, and then define this value here as delta V and this as delta T. And then according to that we can then write down the definition of our acceleration. The letter which we use for this is A, would be in this case simply delta V over delta T. So if we apply this definition here to this graph, then we can say that here we have an acceleration larger than 0, which is really an acceleration. And here in this case we have a value A smaller than 0, which we would call either negative acceleration. We can also call it deceleration. We can also call it slow down, braking, depending in which circumstances you are using that. But the most important thing is that the acceleration can have a positive or negative sign. And another important thing which I would like to highlight here is that when we use this formula here and start at t equal to 0, then our acceleration is simply v over t. And then we can solve this also for v, which at the end leads to v equals to a times t. So this is just another way how to write it. And of course we can also solve it for t, for the time, and this would be then given as v over a. So similar to what we have said in case of speed, we can now define 3 equations which we can use in the near future very often, but of course they are all just one equation written in different ways. So as usual we will make a small example to understand everything a little bit better, and we will start with this car here. Cars are always very good to symbolize kinematic quantities. So here our car in the beginning should rest at a certain timestamp t1, which is equal to 0 seconds. Our car should actually rest and would have a speed of v1 equal to 0 meter per second. And now after a certain time, the same car would have now a certain speed, which means it accelerated by pressing the gas. And then we can here define a speed vector v2, and we only write down the absolute value because it's in one dimension. So we can write here v2, and then the speed should be 10 meter per second, and the time t2 should be equal to, let's suppose, 2 seconds. So after 2 seconds the car has this speed, and now we could calculate the acceleration from that very easily with the definition that we have stated before. So the acceleration A is delta V over delta T, which means we can write this as V2 minus V1 divided by T2 minus T1. And then we can just insert simply our values. So V2 we said is 10 meter per second, and v1 is 0 meter per second, and here we write down 2 seconds for t2 minus 0 seconds for t1. And yeah, then we can see that this just leads to 10 meter per second divided by 2 seconds. And this is easy to calculate. It would lead to 5 meter per square second. And the most important thing here is the unit, because now we have not meter and not meter per second, but we have meter per square second. And this is in general the unit of the acceleration. So we can write here a unit operator on A gives meter per square second, which means every second the speed of the object increases by 1 meter per second. Yeah, and before we talk more about acceleration in general, I would first cover an important topic which we will also use several times, and this is this I call distance calculation. Yeah, so the idea is that when we have a certain acceleration given, we want to calculate the distance that the object traveled from this. So in order to do that, the best possibility would be again to draw a so-called VT diagram, and then we can just draw any graph into this diagram. So it could be, for example, looking like this. It's not necessary that we start at 0, it could start anywhere, but the important thing is that we have a constant acceleration. So the delta v over delta t is constant, and then we can, or if we want to calculate the distance from that, this would be in principle straightforward, but we have to one time write it down to fully understand it. So the distance, we know already from the video about velocity that s or delta s is equal to v times delta t, or s is equal to vt. So we can write here delta s is equal to v times delta t. But I said at that time that if the speed is changing in time, we have to insert the average velocity, or the average speed in this case. Otherwise we will get the wrong distance. And calculating the average speed in this case is actually very simple. First, let me rewrite this equation a little bit. So we can write here v bar, the average speed, times t2 minus t1. This is just the definition of this delta. But then we can now give the average speed v bar. And in order to calculate this, first we choose any arbitrary interval. This could be, for example, here. And we have then here our delta t. And now we can define 2 points here, for example, then here and here, which are just the limits of this interval. And we have here a speed v1 and a speed v2. And here in the center, exactly in the center, we would have our average speed. In case of a linear function, this is very simple. It would be then in principle just given as half of a times t, and in this case then the average value would be 1/2 a t1 plus t2. It's just a simple way how to calculate the average value from two values t1 and t2. Okay, and then the only thing which we have to do at the end is actually to insert that average speed into this equation that we have written down here. And this means then our delta s can be simply written as delta s equals 1/2 and then a t2 minus t1 times t2 plus t1. I just changed the order here because now we can see something important from this equation. And maybe I can write this down here in the corner, because we know from math that that any given product a plus b times a minus b is nothing else than a square minus b square. So and the same we can apply here. So this would then at the end result in 1/2, and then we have here t2 square minus t1 square. Yeah, and this is very interesting because now we have here a way how to convert acceleration into distance. And the important thing is that we have to multiply it with t square, with the square time, and we have to calculate or we have to insert this factor 1/2. Yeah, this is also very important. Otherwise, the distance that we calculate would be by a factor of 2 too large. Now we can take a look at a special case as well. In this case, for example, the time t1 could be simply 0, so we shift everything back to 0. Then in this case, t2 would become simply t, and we can then write down our equation. I will write it down here in the middle. S equal 1/2 a t square. And this is a very important relation, so I would like to highlight this in red. Yeah, so we can now directly convert acceleration into distance. And again, I would like to make a short example to understand it again a little bit better. So this time we will not use a car. We will maybe use a bus, which accelerates with a equals to 2 meter per square second. And then we want to calculate the distance which this bus traveled after a time of 5 seconds. Yeah, so this is then easy. According to the formula which we have derived before, our S would be simply given as 1/2 a t square. And we can insert the values now. 1/2 times 2 meter per square second times 5 seconds squared. This gives 25 times 2 gives 50, divided by 2 would be 25 meter. Yeah, so our bus would have traveled a distance of 25 meter. So now we can continue with our acceleration. And similar to the speed that we have defined before, we can also define a momentary acceleration. Yeah, so until now we always looked at the case where a is equal to constant. It does not change. But of course, we can always have the possibility that that a is also a function of t. So we have here now v over t again. And then we have just an arbitrary graph. For example, it could look like that. And then we want to calculate here this momentary acceleration in this given point. So we have to draw again a tangent, and we have to then define here our interval delta t and our interval delta v. And then the acceleration, yeah, and I think you can guess it already when you saw the other video. When you come from up and from down and you approach or t1 approaches t2, yeah, then this is nothing else than the limit of delta t against 0 of delta v over delta t. So then we can see this is the derivative of v with respect to t, or we can just simply write it as v dot, as we have also done it before. Yeah, and this is very nice. So the derivative of v with respect to t gives the acceleration. And what we can also do, interestingly, is that when we write down a is equal to dv over dt, and v, we said already, is ds over dt. So now we can insert here our v into this v, so to say. And at the end, when we write down what comes out, is a equal to d ds over dt dt. Yeah, and we can summarize this, so to say, as d square s over dt square. Yeah, so mathematically, of course, this is not fully correct, but from the physics point of view, it works. And this is the most important thing. So what we have now is a, the acceleration is equal to the second derivative of the position of an object with respect to the time. Yeah, and again, let's make another example to really get perfectly familiar with that. So let's suppose our position s of t, function of t, would be given as, for example, I just take a random function, minus 5 meter per second. Okay, let's say a second to the power 3 times t to the power 3. So because here is t to the power 3, it also has to be cubic seconds in order to cancel out. At the end, meter has to remain. This is always a good idea to always check the units to make sure that you really get a distance, a speed, or an acceleration from that. And here, then the next term could be, for example, 10 meter squared times t square. And then we could write here, for example, minus 20 meter per second times t. So, and now we want to calculate the first derivative, which is the speed. Yeah, so in this case, we can write t to the power 3. The derivative would be 3 times this constant here. So it would be minus 15 meter per cubic second times t square. And here this term would turn into 20 meter per second squared t. And this term is then the constant at the end, 20 meter per second. So, and then the acceleration we want to calculate in the last step. So what we have to do then is calculating dv over dt in this case, which would be then given as minus 2 times 15, so minus 30 meter per second t, plus 20 meter per second, and the last term just vanishes. Yeah. So this should be, sorry, here we need a square second. So now we have here also from the unit in acceleration, which is perfectly okay. And the only thing, the last thing which we could do now is we want to calculate this acceleration at a certain time, t equal to 2 seconds. And then, of course, we have to write a of 2 seconds, which would be minus 30 meter per square second times 2 seconds plus 20 meter per square second. And this gives at the end minus 40 meter per square second. However, in general, now we always talked about scalars. So in general, similar to speed and velocity, a is a vector quantity. Huh? So we can write a is vector quantity, which means when we want to redefine our acceleration in the form of a vector, we have to write d and then the derivative of the velocity with respect to t, dv over dt, but nothing else changes. Yeah, so similar to velocity, we can calculate the derivative of each component with respect to t. So we can write dvx over dt, dvy over dt, and dvz, the z component over dt, or to write it a little bit shorter, vx dot, vy dot, and vz dot. And here we can make a very simple example, just really to highlight it, but as you see, it will be very simple. So let's suppose we have here our velocity vector, and we can just give some random values again, minus 5 meter per cubic second times t square. Again, this has to be the unit of a meter per second. And here 10 meter per second squared times t, and here we could write maybe 20 meter per second as a constant. Now this is our speed vector, our velocity vector, and from that we can then calculate our acceleration as dv over dt. So the first component, the derivative of the first component with respect to t is minus 10 meter per cubic second times t, and then here we would have 10 meter per second, and here we would have 0. Yeah, so this is just a simple way how to calculate this. And I hope that in general you enjoyed the video, that you learned something new, and yeah, hopefully see you soon for a next video.